There is a signal arriving on Earth right now that took 22.5 hours to get here, sent by a machine older than most of the engineers currently listening for it. No spacecraft has ever operated this far from home. No instrument sent to study interstellar space has functioned this long, this far out, past every deadline its own builders gave it. No model of the space beyond our sun predicted what this particular signal actually contains. It is not noise. It is a pattern nobody can fully explain. Stay with me, because NASA confirmed the details behind this in a peer-reviewed paper, and the explanation is still incomplete. If you're new here, this channel breaks down real space missions with real data. No filler. Subscribe if that's your thing. Let us go back to the beginning. To understand why this signal matters, you first need to understand what Voyager 1 was actually built to find, and why the scientists who designed its mission had every reason to expect something completely different. Voyager 1, Aaron. 1 launched on September 5th, 1977 from Cape Canaveral. 16 days after its twin, Voyager 2, left the same launch pad. The plan was a 4-year tour of Jupiter and Saturn. Nothing more ambitious than that, at least on paper. Budget cuts had already killed NASA's original dream of a single mission visiting all 4 outer planets in one grand tour, so the agency built 2 smaller probes instead, each carrying 10 scientific instruments, a 12-foot dish antenna, and 3 nuclear batteries that convert the heat of decaying plutonium into electricity. At launch, those batteries produced roughly 470 watts, about enough to run a couple of hairdryers. Nobody involved expected the spacecraft to still be transmitting data 49 years later. That expectation wasn't laziness or a lack of imagination. Spacecraft electronics built in the 1970s simply weren't designed with half-century lifespans in mind, and there was no reasonable engineering basis for assuming otherwise. Voyager 1 swung past Jupiter in March 1979, and the flyby alone justified the mission before it ever went near interstellar space. Cameras caught active volcanoes erupting on the moon Io, the first time anyone had observed volcanic activity anywhere beyond Earth. Saturn came in November 1980, with a close pass by the giant moon titan that revealed a thick, hazy nitrogen atmosphere, thick enough to hide the surface entirely. That Titan encounter also permanently tilted Voyager 1's trajectory up, out of the plane of the solar system, ending any chance of visiting Uranus or Neptune the way Voyager 2 eventually did, but sending Voyager 1 on the straightest possible line toward the stars. By the time Saturn's rings faded behind it, the original 4-year mission was already complete on paper. Everything that has happened since, everything this video is actually about, is bonus time nobody budgeted for, time that has, so far, lasted almost 10 times longer than the mission's original design life. The mission's real scientific prize was never just the planets. It was the edge of everything. Scientists had built a solid, testable model of the solar system as a bubble, the heliosphere, inflated outward by the constant pressure of the solar wind, the stream of charged particles boiling off the sun. Somewhere out past Pluto's orbit, that bubble was expected to end, and true interstellar space, filled with its own faint ancient plasma, was expected to begin. That boundary had a name before anyone had ever measured it directly, the heliopause, and the model came with a specific number attached. Inside the heliosphere, plasma density measures around 0.002 of a particle per cubic centimeter, close to a true vacuum. Across the heliopause, and that density was expected to jump roughly 50-fold to somewhere near 1/10 of a particle per cubic centimeter. Hold on to that number. Everything NASA later confirmed about this signal traces back to it. This wasn't guesswork dressed up as science, either. Researchers had been measuring the solar wind since the earliest days of spaceflight, tracking exactly how it thinned as it pushed outward, and the underlying physics of a bubble inflated by an outward pressure meeting. The faint resistance of the galaxy's own interstellar wind was sound, tested, peer-reviewed physics, which is precisely why a 50-fold jump in plasma density became the specific number every scientist on the Voyager team was waiting, patiently, to see confirmed one way or another. Voyager 1 crossed the heliopause on August 25th, 2012, at a distance of about 121 astronomical units from the Sun, 121 times farther out than Earth itself sits. Solar particles the spacecraft had tracked for 3 decades essentially disappeared. Cosmic rays from deep in the galaxy, normally filtered out by the Sun's magnetic bubble, spiked dramatically. Every instrument still working on the spacecraft pointed to the same conclusion. There was just one problem. The plasma sensor built specifically to measure density directly had died years earlier, not long after the Saturn flyby in 1980. Voyager had just crossed the single most important boundary of its entire mission, and the one instrument capable of proving it beyond doubt was already broken. Here's where NASA's confirmation actually begins, and it starts with an accident. Without a working plasma sensor, scientists spent nearly a year arguing from indirect evidence, and the magnetic field data made things worse, not better. By every model, field direction should have shifted the moment Voyager left the solar system, and it barely moved at all. Researchers on the mission's low-energy charged particle team later admitted that based on their own readings alone, they would have said Voyager crossed the boundary a full year before the wider team was willing to announce it publicly, because without direct plasma confirmation, nobody wanted to make that claim to the world and be wrong. Then, in April 2013, the Sun handed researchers a gift. A massive solar eruption sent a shockwave rippling outward through the solar system, and roughly 13 months later it slammed into the plasma surrounding Voyager 1, far out in what should have been interstellar territory. The impact rang the local plasma like a struck bell, and Voyager's surviving plasma wave instrument picked up the tone. The oscillation frequency corresponded to an electron density of about 0.08 particles per cubic centimeter. Read that again. Almost exactly the 50-fold jump the models predicted, confirmed not by a dedicated sensor, but by an instrument built to detect vibrations, catching a shockwave nobody could have scheduled. Picture a sugar cube's worth of space holding a tenth of a particle. Still an almost perfect vacuum by any human standard, but a completely different physical regime from the near total emptiness Voyager had just left, like the difference between an empty concert hall and one with a few dozen people scattered through the seats. Not crowded, but no longer silent. That 2013 detection depended entirely on luck, and everyone involved knew it. Shock-triggered plasma oscillations are rare, and researchers assumed they'd be stuck waiting years between usable readings. Then, in 2021, that assumption collapsed. Stella Acker, then a graduate student at Cornell, and her colleagues went back through plasma wave data collected from 2017 onward and found something that had nothing to do with any solar shockwave at all. A faint, narrow, continuously present emission humming through the readings, month after month, with no dramatic trigger event anywhere nearby. Published in Nature Astronomy in May 2021, the discovery meant Voyager could now track the density of interstellar space constantly, instead of waiting for the Sun to cooperate. And the pattern that emerged from that continuous tracking is the part NASA still hasn't fully explained. As Voyager pushed deeper into interstellar space, sampling density roughly every hundredth of an astronomical unit, the readings showed genuine turbulence. Small-scale fluctuations layered on top of a slow, structured increase in average density the farther out the spacecraft traveled. Sit with that for a second. A supposedly empty void does not hum continuously in a structured pattern. A supposedly empty void does not get measurably denser the deeper into it you travel, for no confirmed reason. Something out there is generating this signal and shaping its texture, and researchers were explicit in their own published findings that the exact physical mechanism behind it remained unconfirmed. Here is where this stops being abstract. Every kilometer of that plasma sits between Earth and the unfiltered radiation of the rest of the galaxy, and the same heliosphere Voyager is now sitting outside of has been shielding human civilization from the full blast of galactic cosmic rays for its entire existence. Understanding exactly how dense, how turbulent, and how structured the space just beyond that shield really is isn't trivia for a science documentary. It's a direct input into every serious plan for sending astronauts beyond the protection of the Sun's magnetic bubble, and into every calculation of how much dangerous radiation actually reaches the inner solar system in the first place. Voyager 1 isn't just exploring a line on a diagram. It's mapping the walls of the only shelter our species has ever had, one uncertain reading at a time. Think about what that means for anyone planning to send humans beyond that shelter someday. A crewed mission to Mars, or further, still lives entirely inside the heliosphere's protection, and every future mission planner trying to model radiation exposure for a multi-year deep space journey is, whether they realize it or not, leaning on exactly this kind of data to know what they'd actually be walking into if that protection ever thinned or shifted. But before NASA could confirm any of that data was even reliable, Voyager 1 nearly stopped talking altogether, and the story of what almost ended the mission is its own kind of impossible. Here's where it gets worse before it gets better. In November 2023, Voyager 1 began transmitting telemetry that made no sense. Not silence, something worse. A repeating, garbled pattern of ones and zeros, as if the spacecraft were speaking, but in no language anyone at JPL could parse. The engineering data, meant to report the health of its own systems, had turned to static. For a machine 46 years into its mission, transmitting from a distance where a single round-trip command takes the better part of 2 days, this was close to the worst-case scenario the Voyager team could imagine. There is no repair truck out there. There is no backup spacecraft waiting nearby. There's only patience, deduction, and code sent one command at a time into total darkness, with a 45-hour wait before anyone finds out whether it worked. No modern update, no wireless patch, no diagnostic app. Every fix has to be composed as raw commands, tested against ground-based replicas of 49-year-old hardware, then fired blind across a gap that grows wider every single day. Engineers suspected the fault lived somewhere in the flight data system, the onboard computer responsible for packaging science and engineering data before transmission. Over months of painstaking work, commands sent, responses awaited 2 full days later, results analyzed, Next commands drafted. They eventually traced the problem to a single corrupted chip inside that computer's memory, one storing a small but essential piece of code. They couldn't fly out and replace it. They couldn't even be entirely certain which piece of memory had failed, because the very system meant to report the failure was the one malfunctioning. And the stakes of getting it wrong were absolute. A single misdirected command, sent to a spacecraft with no working way to confirm receipt, could have permanently silenced the mission, with no possibility of a second attempt, no possibility of ever knowing exactly what went wrong. So they did something almost absurdly elegant, rewrote the affected code and split it into pieces small enough to be redistributed across other sections of memory that were still functioning, reprogramming a 50-year-old spacecraft's brain from a room on Earth 24 billion kilometers away, one careful transmission at a time. In April 2024, after roughly 5 months of silence, Voyager 1 sent back coherent engineering data again. Then, in October 2024, a second crisis. After engineers activated a heater, an automatic fault protection system tripped and shut down the primary radio transmitter entirely, forcing a switch to a backup transmitter untouched since 1981, carrying a signal barely audible against the deep space background. It took engineers until mid-November to fully restore the primary channel. Each time, the same quiet, unglamorous persistence, humans willing to wait 2 days for every single reply, coaxing one more year of conversation out of a machine that, by any reasonable engineering standard, should have gone silent decades ago. Here is what is happening right now in 2026. Voyager 1's 3 nuclear batteries are losing roughly 4 watts of power every year. Less power than a single dim reading lamp, but with absolutely no way to reverse the loss, since the plutonium inside decays on its own physical clock, regardless of anything engineers do on Earth. Of the original 10 scientific instruments, Voyager 1 launched with, only a handful still function, and the mission team has had to make increasingly brutal choices about which ones survive. Both Voyager spacecraft have been bleeding power at that same steady rate since the moment they launched, and it's been enough over the decades to force the shutdown of heaters, backup systems, and eventually entire instruments, one by one, in an order the science and engineering teams agreed on together years in advance, specifically to preserve the most scientifically valuable capabilities for as long as physically possible. On February 27, 2026, during a routine maneuver, the spacecraft's power levels dropped unexpectedly, coming dangerously close to triggering an automatic shutdown that would have forced another lengthy, risky recovery. Rather than wait for that failure to happen on its own terms, the team acted first. On April 17, 2026, engineers sent the command to permanently power down the low-energy charged particles instrument, the very detector that helped confirm the 2012 heliopause crossing in the first place, leaving Voyager 1 with exactly 2 working science instruments, the plasma wave system that caught the still unexplained hum, and a magnetometer tracking the shape of the interstellar magnetic field. 2 instruments. Out of 10, 49 years in, still returning data, according to the mission's own project managers, from a region of space no other human-made object has ever reached. And power isn't even the only failure mode the team is managing. Some of the thrusters that keep Voyager 1's antenna aimed precisely at Earth have clogged with residue built up inside their hydrazine fuel lines over decades of use, and the spacecraft no longer has a working backup system for attitude control. Suzanne Dodd has put it bluntly. Everything left on board is single string now, meaning there is no redundancy left to fall back on if any one critical system fails outright. The team's next move, nicknamed the Big Bang, is a coordinated swap of several power-hungry components for lower power alternatives, executed all at once. It was tested first on the less power-starved Voyager 2 in May and June of 2026, and if that test succeeds, the same maneuver is planned for Voyager 1 no earlier than this July, which means that as this video reaches you, engineers may be performing delicate surgery on a computer 25 billion kilometers away, with a 2-day gap between every incision and every confirmation that it worked. And in a few months, something happens with no ambiguity at all, a date locked in by nothing more complicated than distance and the fixed speed of light. On November 18th, 2026, at 2:16 and 7 seconds in the morning, Pacific Standard Time, Voyager 1 will sit exactly 16,094, 799,096 miles from Earth, a full light day away, the distance a beam of light travels in 24 uninterrupted hours. Suzanne Dodd, the Voyager project manager at JPL, has described what that will actually mean for the people running the mission. If she sends a command and says, "Good morning, Voyager," at 8 in the morning on a Monday, she won't hear the reply until 8 in the morning on Wednesday, not because anything is wrong, because that is simply how long it now takes for a whisper to cross the distance between a machine built in 1977 and the hands still tending it today. To put that milestone in perspective, when Voyager 1 crosses the one-light day mark this November, it will be more than 5.5 times farther from Earth than Neptune ever gets, further than any spacecraft in the history of the space age has traveled and still managed to talk back. There is no scenario in which that date moves. It isn't a prediction, and it isn't a projection built on assumptions that could change. It is simple arithmetic, running on rails, counting down in the background of every other story this video is told. Now, the part that doesn't resolve neatly, because it genuinely hasn't resolved yet in the published science, what exactly generates that persistent plasma hum Voyager has been picking up since 2017 is still not settled. The 2021 Nature Astronomy paper that first identified it lays out competing explanations, rather than a single confirmed answer. The emission could result from thermally excited plasma oscillations, small random vibrations that occur naturally in any warm plasma, with nothing dramatic driving them, or it could be a form of quasi-thermal noise, a broader statistical hiss produced by the constant jostling of charged particles throughout the local interstellar medium. Both remain physically plausible. Neither has been definitively confirmed as the sole cause, and the researchers themselves were explicit that a full answer would need either new Voyager data or an entirely new interstellar mission to resolve it properly. What most people are not seeing when this story gets told is that we don't fully know yet isn't a failure of the science. It's the honest current status of a measurement being taken somewhere no other instrument has ever operated long enough to double-check. There is no second Voyager-class probe currently operating in interstellar space to cross-reference the reading against, no independent instrument anywhere confirming or contradicting it. For now, and likely for years to come, this single, aging plasma wave detector is the only source humanity has for this particular piece of the universe, which means the honest answer to what's causing it really is still open, whether that's a satisfying place to end a story or not. Step back from the plasma readings and the power budgets for a moment, because there's a larger pattern worth sitting with here. Voyager 1 was never designed to still be answering questions in 2026. It was built to survive a 4-year tour of 2 planets, using engineering standards from before the personal computer existed, using memory measured in kilobytes rather than gigabytes, using a transmitter. Engineers now have to wake gently, aware that any wrong move could end the conversation permanently. And yet, it's that same aging, power-starved machine that keeps handing scientists genuinely new physics. A heliopause boundary confirmed by cosmic accident, a persistent interstellar hum nobody predicted, a density gradient that still doesn't perfectly match the models built to describe it. This is the pattern underneath almost every real leap in how humanity understands its place in the universe. Not a single triumphant discovery arriving on schedule, but old instruments pushed past their intended lifespans, returning data nobody built them expecting to receive, forcing the models to catch up to the machine instead of the other way around. Think about what that means for how the next 50 years of exploration get planned. Every mission NASA launches today is designed and budgeted against a specific expected lifespan, and Voyager 1 stands as a permanent, uncomfortable reminder that the most valuable data a spacecraft ever returns might not arrive until decades after everyone who built it has moved on. The scientists reading Voyager's plasma hum in 2021 were not the scientists who designed the plasma wave instrument in the 1970s. Some weren't even born yet. That's not a footnote. That's how this kind of science actually works. One generation builds the ear, and a later generation finally learns how to listen with it. And it isn't only the science that outlasted its original planners. The entire operating culture around Voyager has had to survive too. A small, aging team of engineers, some of whom have spent their entire careers on this one mission, translating decades-old documentation, keeping alive the institutional memory of a computer architecture that most of the industry stopped using before today's software engineers were in school. That knowledge, as much as the plutonium in the batteries, is the actual fragile resource keeping this conversation with interstellar space alive. There is a photograph still sitting in Voyager 1's memory of a pale blue dot suspended in a single sunbeam taken on February 14th, 1990, the last time the spacecraft's cameras ever turned to look back at where it came from. Engineers shut those cameras down permanently weeks later and stripped the imaging software out of the spacecraft's memory entirely, freeing up power for the instruments that mattered more for the road ahead. Voyager 1 has not photographed anything anywhere in the 36 years since. It gave up sight so it could keep listening, and what it has heard in the decades since that last glance homeward is a universe that does not go quiet just because there's no one there to witness it. A plasma humming faintly in the dark, a density rising and falling in patterns science still can't fully account for, a signal that keeps arriving one day later than whenever it was actually made. Bolted to the same spacecraft, a gold-plated record still carries greetings in 55 languages and a map showing the way home, traveling outward now with no one left to hear it, indefinitely, long after the last watt of power finally runs out. Somewhere in the ship's frozen electronics, that photograph and that hum exist as the same kind of thing, a message sent outward with no certainty anyone would ever be equipped to receive it, waiting patiently in the dark for someone, someday, to finally understand what it was trying to say. So here's everything in one breath. Voyager 1, launched in 1977 on a 4-year mission, turned its cameras back for one final look at Earth in 1990, then crossed into interstellar space in 2012. A crossing NASA could only confirm a year later, thanks to a lucky solar shockwave ringing the plasma like a bell. In 2021, researchers found what the models never predicted, a persistent, still unexplained plasma hum that has let them track interstellar density continuously ever since. A catastrophic computer glitch nearly ended the mission in 2023 and 2024, fixed by engineers reprogramming the spacecraft's memory one careful 2-day delayed command at a time. Today, only 2 of Voyager's original 10 instruments still function. Power keeps bleeding away at 4 watts a year. And in November, the spacecraft crosses the 1 light day mark, a threshold that turns every future exchange with it into a minimum 48-hour round trip. And the exact cause of that hum it first caught in 2017 is, right now, still not fully resolved. One lone spacecraft, 49 years old, still the only witness humanity has to that particular corner of the dark. If any part of this made you want to see where the story goes next, because there is a next chapter, whether the Big Bang power swap saves Voyager 1 this July or the mission finally goes quiet trying, hit subscribe and turn on notifications, because I'll be covering that outcome the moment NASA confirms it. One question before you go: would you rather NASA spend its remaining resources keeping this 50-year-old machine alive a few more years, or accept its silence and put everything into building something new to take its place? Let me know in the comments below. I read every single one.